Not for all. I'm not comparing all for a given LED. Forward voltage. What is VF? Forward bias. Forward biasing voltage or forward bias across the diode. Forward bias voltage. As the increased forward bias, what should happen? Go for. So shall I summarize here? As the increased forward bias, you have to go back here. Let's come for here. As the increased forward bias, without depletion increases, more majority carriers will cross the junction. Number of majority carriers crossing the junction will increase. Without depletion decreases, number of majority carriers crossing junction increases, more recombinations will occur. So, and what happened to number of photons emitted will increase. So, intensity of LED will increase. Agree? Simplest way. No need to struggle anything. As the increased forward bias without depletion increases, more majority carriers cross, means more number of electrons will move from N to P type, more number of photons will move from P to N type. Fine. Then more recombinations will occur. One recombination, one photon. So more photons will come out. So what will happen to intensity of LED will increase. I agree this. So I'll write explanation also. In books it's not there. So how the graph we can expect here? What is the possible graph? The possible graph will be this one. Put it like this. So this is some forward voltage. So for some of the LED I'm taking, so let it be 2 volt. I think least from where we are starting 1.2, no? Infrared 1.2. Let me go for gallium arsenide. Approximately I'll write 2 volt. And then I'll keep on increase this forward bias. I know how much needed to forward bias a diode. 2 volt. I'll increase it forward bias. Then the intensity should increase. Any reason? So I'll give the reason like this as forward bias. Shall I show up arrow? Increases as forward bias increases. Number of, let me write sentence only. Why that? As forward bias increases, number of majority carriers crossing a junction increases. Then majority carrier crossing a junction increases. More number of, there'll be increase in. The core idea is what I'm explaining. There will be an increase in recombination. There will be an increase in recombination occurs. So, and hence number of photons emitted increases. If number of photons increases, we know intensity of light emitted by LED is directly proportional to number of photons emitted by LED. So what do you expect? Therefore, the intensity of light will increase. It is justified straight line. And then afterwards, you'll be surprised as the increase forward voltage, it start decreasing. Then we'll take curve. So how that variation of curve can be of any shape. So it can come like this also. can come like this also. Let's not bother. If you want, I'll put dotted line. That's why the books open to, and afterwards it'll be constant. After say around 9 volt, though you increase the forward bias voltage across the diode, the intensity will remain constant. Now, what should be the reason? Increases but remains constant. Increases but remains constant. So how come here forward will increase, intensity increase, here nothing? Now what is the reason for that? As we increase forward bias further, let's come for this one. As I increase forward bias further, what happened to the number of majority carriers crossing? The number crossing will increase, and at the same time, what will happen to the speed with which majority carriers moving? Sir, why you are bringing speed? Okay, now you go back to the current density. As you will increase the EMF of a cell, what will happen to the drift velocity? The drift velocity is directly proportional to the applied EMF. Ohm's law. The drift velocity is directly proportional to the applied field. Am I right? Will agree this? So therefore, as I increase this EMF, the speed with which majority carriers cross the junction will increase. Now the speed is very high. Means very high means not don't say again equal to speed of light. As the speed increases, the holes find very difficult to catch that electrons. The holes will find very difficult to catch that electron. Means suppose say a person is slowly moving and you are standing here. Can you catch him when he's moving, when he's just walking or moving slowly? You can catch him, no? If he runs with high speed, what is the probability of you catching him? Means you are there, just you will pass nearby it. What is the probability of catching him? Will be less, no? So I think I'll try to put it like this. Huh? Just wait, I'll switch on the light. What is the actually meaning of this? So there's a hole, there's a hole, there's an electron. Huh? There's a hole, that one. So earlier it is, this mobile is electron. Hand my fingers, this everything, what happened, the fist will become all that one. So when it is electron moving slowly, I can catch easily, no? You can catch easily. Instead that, so what is the probability here? No, you can see. If I slide mobile with high speed, so what is the probability of catching it? Decreases, no? If it moves slowly, I can catch it. So you can try with the ball, no? Suppose say you ask somebody to throw the ball and try to catch it. It should pass through you and try to catch it. You find difficult. Instead of moving slowly, you can catch it very easily. Getting the logic here, that's what you should apply here. So it is like this. Huh? I can catch it, no problem. If I move with speed, no, so probability of catching now mobile will be difficult here. The same thing happens for the hole. So at the speed of, as the increase forward bias, the speed of majority carriers increases, then the rate of recombination decreases. The probability of recombination will decrease here because of high speed of majority carriers, and because of that, what means the intensity decreases. Getting this one? So these are the, I think in NCRT has just given that as you increase forward bias, intensity decreases. Reason for that is what I'm just trying to explain. As forward bias increases, the speed of majority carriers increase. The speed of majority carriers will increase. Because of this, a hole fails to capture fast moving electron, a hole, no, where is a hole? A hole in p type fails to capture fast moving electron moving from n type to p type. So therefore hence recombination decreases. Number of photons emitted decreases, and hence and therefore we'll write it, and therefore intensity decreases. This you can buy LED, how much? Around 5 rupees, 2 rupees it will be there. Nowadays we have a Duracell, no? Duracell. So you purchase of 9 volt or something Duracell. I think it will cost you around 35 rupees. You purchase one resistor, it will cost you around 1 rupees. That one. So as you vary the EMF of cell by varying the resistance, so definitely you can see that. Or you purchase, you connect one 1.5 volt across the LED, you'll get, it will be bright. When you connect 9 volt Duracell across the LED, the brightness will be less. You can see clearly. These are not something theoretical. We can see practically. I think in the revision when college opens, there I'll show it. Or I think in YouTube you can type it. You have videos. The lab they'll show it. If you want, you can see that one. So this is the main reason why the curve should be like this here. So shall we put it intensity directly proportional to forward voltage? Fine, but not all the time. Huh? For higher forward voltage, the intensity will decrease here. So the reason what I gave it. This is, I think, 1. This expression is for 1. This is for 2. The points we have written, for different parts of the graph, this explanation. Okay, so there's a basic idea. What are the different colors? Means let me compare the forward bias of. There's a graph already they've asked in. Let me plot the graph. In infrared should not be visible, no? So therefore, infrared is not visible. I'll not show it. Then red color. Different LEDs in one graph only. I'm trying to show the different LEDs in one graph only. Amber means it should be yellow, no? Some sort of orange color it will come. Amber, orange, red is called as amber. It's a very important. This one. Next we have yellow. Green. Blue. White light. Okay, well, ash color we have here. There's in fact white. I'll write nearby that one. So these are things. I think the color itself, white, and there's a infrared. There's a forward current, and there's a forward voltages. or what you can call knee voltage. What is VF? Knee voltage. I'll call this as forward voltage or knee voltage. So as that particular, for different colors it will be different. So there's a blue, green, yellow, amber. This is red. Why it should be? The reason for this, the band gap, and based on the band gap, there's the forward voltages. So shall we put it one simplest way? As the wavelength decreases, the forward voltage required will increase. Agreed? The white one, you take it out. It'll be very confusion. So just take it out. This you don't bring in much into discussion. Compare only these colors. It will be much easier for us. So as the wavelength decreases, you can see this. The forward voltage required to forward bias LED will increase. This I think already asked in mains. You have to be careful. Not this is for different LEDs. VI characteristic, forward bias, VI graph for same LED cannot exhibit all. I think by this time you should try to understand. It's not about one LED. Different LEDs, I'm just putting in one single graph I'm comparing. So forward voltage, the new voltage to forward bias LED will be different for different colored LEDs. That's what I mean to say. So the forward voltage new voltage to forward bias different LEDs, different colored LEDs will be different. This was already asked. It means possibility of asking again. Just do remember. What about the circuit? Okay, this is about the theory. What about the circuit conditions? When you reverse bias, you don't get any light. Let me finish off that also. So when you reverse bias, it will get damaged here. No light. No light. It is what? Light will come. So when you operate in this region, it will start emitting light. So therefore, no question of reverse biasing the LED. When LED is reverse bias, hardly will get any light here. Better say no light. In book they say like no light here. Microampere. This is the reverse voltage, and breakdown will come and get permanently damaged here. So usually what is reverse breakdown voltage for LEDs? It will be of order 4 volt. So that's why we never reverse bias the LED. And if you just type in book, no, they have made that material everything. So it will be like this. This will be P type, this will be N type. The one which is longer lead will be P type, this will be N type. And it will be, I should protect it. So I'm protecting it by a transparent cap. It is plastic cap. Inside there'll be LED material. And what this material will do, will emit light in all direction, no? This one. So therefore, to overcome that, I will come with here like a reflector, mirror. I'll keep it here. So any light that is emitted in downward, it's of no use, no? Suppose in mobile, it will emit light. Some of the light will go into the mobile, which is of no use. So therefore, I'll place a reflector. What that reflector will do, will send back the light here. So there's a use of this reflector. What is the green color one? It's a mirror. So what is the duty of it? Because any light emitted here downward, it's of no use. So only this light will be useful for us. So therefore, I'll put one reflector. So what is the use of reflector in the LED? So that the light should be emitted in one specific direction. Means the light emitted in this direction is of no use, because this will come into the mobile. Are you getting? No, it will come into the mobile. This part will come into the mobile. So I should get light from the mobile, no? This one. So therefore, open here we use reflector. Go the idea. Reverse bias is of no use. Will not get any light in forward bias, yes, will get a light only when you come for certain range. Why do put like this? If the forward voltage is 2 volt, no, then what about here? It will not emit light. That's why we have put a dotted here. In books open, they've shown a dotted. Only when you forward bias, it starts emitting light. And as you increase forward bias, the intensity will increase. And at certain value, it will almost remain constant due to like a increasing the speed of the majority carriers. There's about the idea like this. Okay, now if you go for circuit, how the type of questions here? It's similar to like an ordinary diode, like how we forward bias. No, the same set of numericals will be asked for you. How we had ordinary diode, the similar numericals will be there. So how to forward bias this LED? I'll always connect one resistor in series. Then this is a cell. Let this be say like a some around 8 volt. Now I'll bring that resistor here. Now it starts emitting light. There's a symbol what we show for LED. If you have arrows nearby it like this away, it is nothing but what it is, light emitting diode. So what is the forward voltage of such a diode? Let me take 3 volt. And let this be 70 ohm. Then how much of current will pass through it? How much of current? So how to calculate that current? Let me calculate the current. So what is IF is equal to E minus VF by RS. If they give any forward voltage of LED, say some 5 ohm, 10 ohm, that you can add up here. So let me take this ideal. What is VF? Forward voltage. In place of LED, replace with a cell again, similar method. So this will be 8 minus 3 by 70. 5 by 70 ampere. Then I want what is the intensity of the light at a certain point, say like a. How to calculate intensity? This will be like a source of light, no? So what is the power emitted by the LED? Should be equal to VF into IF. What is VF? 3. 5 by 70 is the power. Then what is the intensity at a distance? Capital I is not current. Capital I is intensity. Power of LED by 4 pi x square. So how the LED will behave like a point source. Here what is the idea? LED and you know for a point source of light what is the intensity? Power by 4 pi x square. What is the power of LED? Forward voltage into current through it. I'm assuming LED is 100% efficient, but practically what will happen? The efficiency will be around, you can say like around 85%. It's very good. Where do 15% will go? There'll be some heat will be generated because the forward resistance will be there. What is the forward resistance? The material, the P and N regions will offer some resistance to the flow of charges. No, so there'll be some heat will be generated. Not that, you know. So therefore, I'm assuming that 100%. If we say like efficiency is 80%. So what you should do? 0.8 you should write here. So what we are assuming? Efficiency of LED is 100%. But practically what will happen? It should be only around 80-85%. It's good, no? Only 15% will be heat generated. And it all depends upon the forward resistance. I'll see that the forward resistance I'll minimize by some methods. But at the most maximum in industry, what we have 85%. That's why you see LED, no? And you see how much needed? 3 volt is very small, no? Like that, if I connect some 10 LEDs, that will become equal to one bulb. I think that's what now we have, no? So if you look at the ordinary tube light, the tube light what we have, the gas, hydrogen gas filled up tube lights what we have, and you look at the LED bulb. So what is the LED bulb here? So I will go for combination of 10 LEDs. This tube light cost, okay, that one, of course, little bit, this will come around nowadays 300 rupees, no? Tube light, this is also not that cheap, 150 rupees. What is the lifespan of this? 3 years. What is the lifespan of this? 50 years. If you use properly, they say that warranty is around, for 3 years, minimum warranty it will be there. If you actually use it, no, it will come 50 years. And what is the power consumption? If this consumes 100 watt, this will consume around, you can say, 2 watt. How much of electricity we are going to save? Huge electricity. That's why street lights, now we are going for LED. We are going to save power like anything, because how much needed? Just 3 volt. 3 volt is something very small, no? I think now best thing when electric power not there, the mobile only we are using, no? The mobile torch light, it is there. So what is LED only? So if you use that, I think it will come exactly. Depends upon mobile. I'm having mobile, it will come around 16 hours. If I just only put that torch light of the mobile, and it can easily illuminate my room. It's something very good, no? And how much I spend energy to charge mobile once? I think around 1 rupee. For full charge of mobile, how much it will cost you? 1 rupees. And that 1 rupee what pen will help us. So LED is something you can select. It's going to revolutionize the way of lighting. And tube lights, different shapes not possible. LED, any shape. That's why you see in mobiles that blink, red, blue, green colors will come, no? On in laptops. Everywhere it is coming to picture now. It's something you can say like a slowly what happened, it is bringing huge revolution. Okay, this is about the how to calculate the intensity at a given point. So we can use this one. These are the types of questions will come here. I have small two topics: photodiode, solar cell. Both are same. Shall I continue or your wish? Shall I continue? I think all there you can reply back. Shall I continue? I'll finish off because again next week